All right, guys, welcome back to another daily algebra journal. We're looking now at section 8.6, the very last section in chapter 8. So if I'm reading this title, which I really should, we're looking at comparing linear, exponential, and quadratic functions. So what does that mean for you? Well, since we're just comparing, we're not really focusing on how to graph anything. We're just taking a look at, well, what do we know, generally speaking, about these three function types: linear, exponential, and quadratic. So let's start by looking at the first exploration. How can you compare the growth rates of linear, exponential, and quadratic functions? The answer here, of course, is going to be we're just going to take a look at them. So the first exploration, we've got 3 cars starting at the same time. The distance traveled is going to be y miles. So when I look at this graph, these charts down over here, this is distance right here, these first columns. Obviously, or maybe not obviously, whichever has the greatest value in that second column is going to be the one that went the furthest. Also, notice that we're talking about t minutes, so we're only going from 0 to 1 minute. And, well, how far did they go? This first one's pretty easy. Y equals t, so if t is 0, y is also 0. If t is 0.2, 0.2, 0.4, 0.6, 0.8, and 1.0. Now the second one over here, y equals 2 to the power of t minus 1, we call this an exponential function. I can tell it's an exponential function because the independent variable t is appearing as an exponent. Okay, if the independent variable is an exponent, you're looking at an exponential function. That's why they get their name. We're going to go take a look at our Desmos window real quick. And what is our Desmos window going to tell us? Well, right now we have y equals t, and we're going to switch to y equals 2t, 2 to the t power minus 1. Okay, so notice how this time we have a gentle upward sloping trend. I'm not even all the way on camera. It's an upward sloping trend. So I think we're at every intervals of every 0.2. So what do we have here? At 0.2, we got, I think, 1.5, 1 point something, 1.15. No, 0.1, yeah, 0.15. And then over here we get 0.31. Then at 0.6 we get 0.51. And then over here at 0.8 we get 0.74. And over here at 1 we get 1. So let's take a second, put those into our chart. Okay, so in the chart now, okay, I did a little bit of refinement here, and as we take a look comparing these two, at 0.2 seconds, the linear graph is faster. At 0.4 seconds, the linear graph, has gone farther. 0.6 seconds, the linear graph has traveled further. 0.8, same thing. And then once we get to 0.1, I think I made a mistake here. This should be 1.0. The two graphs have traveled the same distance. Let's do the same thing for y equals t squared. T squared looks like this graph. Okay, so this, this kind of looks like the exponential curve. It's still got that slopingness to it. And here at 0.2 we get, I don't know, 0.04. At 0.4 we get 0.16. At 0.6, we get 0.36. Over here at 0.8, we get 0.64. So let's put that in the chart, and then we'll compare. Well, now that we have that in the chart, yeah, at 0.2, at t equals 0.2, it looks like the fastest one is linear, second fastest is exponential, and the slowest is quadratic. Over here at 0.4, again, fastest. Now this has changed. The quadratic is now the, no, I'm sorry, it hasn't changed. The next fastest is exponential, and then the slowest is quadratic. And then at 0.6, I think we have the exact same order, 0.8, same order again. So it looks like as we read this chart from left to right, we are in the order that they finish, or their apparent speeds. So take a second to put these graphs in the chart. I'm going to go do that for you as well. Wait. Put them in the chart, man. Put them in the graph. Hurry. Okay, so this is what we're looking at. As you can see, the quadratic function was in red. It looks like it's traveled the least amount of distances. And then the exponential curve is in green. It's covering just a little bit less distance than the linear function. The linear function is blue. That seems to be covering the most distance until at t equals 1, all three of those curves meet up again. All right, so what does that mean for us? Well, now let's take a look at the curves. And I'm not going to go ahead and fill in all three of these charts, but what I am going to do is I'm going to take a look at Desmos and see what happens. So we're going to get all three of those graphs on Desmos at the same time, and let's see what happens. Okay, so we're going to make all three of these live, and as you can see, I didn't graph it completely crazily. That actually looks pretty good, right? And what we're going to do now is we're going to expand this graph so that, well, what was our minimums going to be? Our t's are going to go from 0 to 5. Okay, so our t is in the x-axis, so we're going to go all the way to, let's go to 6. And having some idea about what this looks like, I know that we should go to about maybe 35. So we can take a look at how these graphs behave. All right, so let's take a look at these two graphs then. Well, now who's the fastest? Okay, so it looks like starting at t equals 1, that red graph is now the slowest. Or not the slowest, but it covers the least amount of distance. Okay, it has that constant rate of growth. It's never getting it's never getting particularly faster. No, it's not getting faster at all. It just keeps on growing at the same rate. However, that blue curve starts off second, well, no, starting here, it is the second amount of distance traveled. And then right here, the blue graph overtakes the green graph. So the quadratic goes from worst to first, and then it settles down into second place. Okay, so where do these two graphs actually meet? It looks like they meet at 4.257. Is there anything special about that number? Well, I'm not 100% sure about that, but they are meeting. So the moral of the story here is that even though the exponential curve starts off as the slowest, eventually the exponential curve is going to be the fastest growing curve. And I think if we go back to that screen and we zoom out even more, I think it's going to be even more dramatic. Take a look at this. Okay. Once we look over here at t equals 10, the quadratic curve is at 100, but the exponential curve is literally off the chart. Okay, so the exponential curve starts off by growing slowly, and then eventually it literally explodes. And I don't mean literally as in the sense of it actually explodes, but the growth rate becomes what we would say is uncontrolled. The growth rate, this is actually really topical for us. This is the kind of growth rate that we expect from things like infectious diseases. They start off growing really slow, and then before you know it, everybody is infected. So this is your moment of coronavirus, isn't it? You got all your points plotted? I do too. Let's take a look at the curves that we got. This number one, notice how it has a change in direction. So the only one of the graphs that we were looking at that has a change of the direction, decreasing to increasing, is a quadratic graph. That's quadratic. This one over here looks like a ski jump, so we're calling this exponential. And let's see this one over here. Now this one looks to me like it has a ski jump, but it's just kind of backwards, isn't it? So this is actually what we would call exponential decay, which is the opposite of exponential growth. So this too is exponential. This one, of course, looks like a line, so we would call this linear. All right, that's not too bad, right? All you got to do is graph points. Tell me what you see. Here we go. We can tell if are these linear, exponential, or quadratic. Let's take a look. First thing I want you to do is look at the differences between the y values. So for example, from 7 to 4, that is minus 3. From 4 to 1, that's minus 3. From 1 to negative 2, minus 3. Minus 3. So it's the same difference. So that means that this is linear. Okay. Same difference means linear. How about over here? Is it the same difference? 6 to 2, that's minus 4. 2 to 0, that's minus 2. 0 to 2, that's plus 2. 2 to 6, that is plus 4. So what do you think? It's not all the same, so it can't be linear. I'm looking at this function. It's going down and then going up. Minus, minus, plus, plus. So that tells me that this is a quadratic. There's a change in the direction. Okay. Over here, number 7, same idea. We've got minus 2 to minus 1. Actually, let's take a second and put that in a chart. That's a pretty busted looking chart, I admit. Negative 2, negative 1, 0, 1, 2. And it's very important that our x-coordinates follow a pattern. Okay, if the x-coordinates don't follow a pattern, we wouldn't be able to tell what's going on. So negative 4, negative 1, 2, 5, 8. Well, first of all, it seems to be always increasing. So this isn't quadratic. Let's take a look at the difference. We actually call that delta y. So delta y here is negative 3. Plus 3. From negative 2 to 1, that's plus 3 again. From 2 to 5, that's plus 3 again. From 5 to 8, that's plus 3 again. Our delta y is constant, so this is a linear function. We'll do the same thing over here. We'll make a chart. Actually, I'll make a chart, and you guys, I'm going to pause it, and Are you ready to go? You're graphing, right? Making a chart? Okay, 3, 2, 1. Our chart, we're going to look at our delta y's now. Delta y from -9 to 0, that is +9. From 0 to 3, that's +3. From 3 to 0, that's -3, and then -9 again. We have a change in direction, so this looks like a quadratic. And I don't know how to spell quadratic. A ball is dropped 305 feet. The table shows the height. Let t represent the independent variable. Tell where the data is modeled with a linear, exponential, or quadratic. So the first thing I want to do is I want to do a delta. Now I would say delta y, but the independent variable here is h. So we're looking at a delta h, a change in h. Go ahead and write that. Delta h, delta h, delta h, delta h. Pause and wait. Pause it. 3, 2, 1. The delta h's here are not the same. Notice that, they are increasing, or rather decreasing, all the way down the line. But what is the pattern here? So first of all, clearly not linear. That's pretty obvious. Less obvious is that it's not quadratic. And the only thing I can say against a quadratic is we don't have evidence here that this function is increasing and then decreasing. There's no evidence of a change in direction. Now, the thing that makes me say that this is exponential is the following. Let's take a look at this. How do I get from 16 to 48? Well, 48 is -16 times 3. Okay. How about from 16 to 80? 16 to 80 is -16 times 5. And how do I get from -16 to -112? Well, that's -16 times 7. Okay, so we seem to be always... So these differences in delta h, these are related through multiplication. So because they're related through multiplication, we're looking at a function that is exponential. So there we have it. We've got the last section of chapter 8 underway. Remember, this last one was not so much multiplication or division or any kind of mathematical operation. It's just taking a look at the relationship. Remember, exponential functions, they grow really fast, and linear functions are growing pretty slow. So that's the end of the day today. Have a good one, and you should be expecting your chapter 8 test any minute now. See you next time.